lesson, I'm going to be talking about a laboratory technique, a tool that's called Photoelectron Spectroscopy. And what PES, or Photoelectron Spectroscopy, allows you to do is to determine the electron configuration of an atom, of the electrons of an atom. This is a PES, and its purpose is to identify where electrons of a single atom are placed. Okay? So note that the y-axis represents the relative number of electrons, so each peak's height represents how many electrons are going to have a specific ionization energy. Now also note that the closer an electron is to the nucleus, the more energy needed to remove that electron. And so if you notice, at 349, that represents the electrons that are closest to the nucleus, while the 0.42 and the 2.38 are much farther away from the nucleus. And so as a result, we know that the 349 peak, that first peak on the left-hand side, that's going to represent 1s2. Because remember, 1s is the orbital that is closest to the nucleus, so we know that it's going to be 1s2. So the next peak, the 37.1, it is the next closest to the nucleus, therefore it's going to be from the 2s subshell. Now notice, because it's the same height as the 1s subshell, it's going to have 2 electrons. So the electron configuration for that is going to be 2s2. So we've got 1s2, 2s2. Next is going to be 2p. And notice height-wise that peak is about 3 times as large as the first 2 peaks. Therefore, it's going to have 6 electrons in there. So the electron configuration is going to be 2p6. The next sub-level is going to be 3s. Notice it's the same height as the first 2, therefore there are going to be 2 electrons there. The next one is 3p. Notice it's the same height as your 2p, therefore it's going to have 6 electrons there. For the last one, it's going to be 4s, and notice since it's half as tall as the peaks that have 2 electrons, it's going to only have 1 electron. And therefore, this entire PES allows us to determine the electron configuration for this atom. It's going to be,
so the PES graph that we were looking at allows us to compare the amount of energy that's required to remove electrons in order to determine the electron configuration for an atom. So specifically, the first peak that you see, that corresponds with your 1s, because the electrons are much closer to the nucleus and therefore require more energy to remove. Now, a type of question that can be asked is, well, if we know the amount of energy that's required to remove an electron, if we provide more energy than that, what happens to the electron? And the answer is that the electron will actually fly off. And in order to create your PES, that's actually what's measured, the speed at which that electron is actually flying off of the atom. So for this practice problem, it tells you the amount of energy that's required to remove 1 mole of electrons. Okay? And what it asks is, if I provide 254 nanometers of light, what is the maximum kinetic energy that the electrons will have? So the energy required to remove the electrons, which you'll soon learn is called your ionization energy, that is 208.4 kilojoules per mole. Okay? So 208.4 kilojoules per mole is required. And the question becomes, all right, well, if I provide 254 nanometers of light, how much energy will that be? And is that more than what is required or less than what's required? If it's less than what's required to remove the electron, then the electron will not be removed from the atom. If it's more, then any extra energy will be converted into kinetic energy. And so this relates to PES simply because we're comparing the amount of energy that's provided with how much is required to remove an electron. So our task in answering this question is to first convert 254 nanometers of light into kilojoules per mole in order to compare it with the energy that's required. So what I'm going to do is I first need to, because I need to use my formula C equals lambda times nu, I need to convert into nanometers. So I'm going to first convert by putting nanometers on bottom and meters up top. This is one of the pretty much just 3 relationships that you need to know as far as prefixes are concerned. So we know that 1 meter is 10 to the 9th nanometers. Okay, and so you end up just taking 254 and dividing by 10 to the 9th. and you get 2.54 times 10 to the negative 7th meters. Now I can convert that into frequency first using C equals lambda nu, and then once I have frequency, then I can figure out energy. So I'm going to use this formula. C is either 2.998 times 10 to the 8th, or you can just round to 3.00, that's fine. So I'm going to use 3.00 times 10 to the 8th, which is my speed of light, divide that by my wavelength, which is 2.54 times 10 to the negative 7th, and I get my frequency, my nu, which is 1.18 times 10 to the 15th seconds to the negative 1. Now I wrote out these answers for you to see. What I do is I keep it all in my calculator, because if you keep rounding to the correct number of sig figs, which in this case is 3, you're going to end up over rounding your answer. So just keep it all in your calculator. Now that I know my frequency, I can figure out my energy by using the formula E equals h times v. H is Planck's constant, my nu or v is my frequency. So I'm going to just multiply Planck's constant by the frequency I just got. Keep in mind, I'm not actually multiplying by 1.18. I'm multiplying by what I had in my calculator that's unrounded. And so the energy I get is 7.83 times 10 to the negative 19th joules per photon, but I still keep it in my calculator. That's the trickiest thing that you have to remember, is that you're in joules per photon, not joules per mole. So whenever you're dealing with wavelength and frequency, when you find energy, it's implied that you're in joules per photon. So now what I need to do, because I need to get into kilojoules per mole, I first need to get into joules per mole. So I'm going to convert. I have joules per photon, so I'm going to put photons on top, moles on bottom. I have 6.022 times 10 to the 23rd photons for every 1 mole. And so when I multiply, I end up getting 4.72 times 10 to the 5th joules per mole. Well, I want kilojoules per mole, so I know that I need to actually divide by 1,000 to get into kilojoules. You should be able to do that in your head now. You shouldn't have to actually show your setup for that. So if I divide by 10 to the 3rd, I end up getting 4.72 times 10 to the 2nd kilojoules per mole. So let's go back and make sure we understand what all these numbers mean. 208.4 kilojoules per mole are required to remove that electron, and that corresponds with the PES that you saw when you guys were working to determine electron configuration. 472 kilojoules per mole is what I actually provided. So I provided more energy than was actually needed. So to determine the kinetic energy of the electron when it's removed from the atom, all you have to do is take 472 and subtract 208.4 from that, and all of that extra energy is going to be kinetic energy. So the kinetic energy is going to be 264 kilojoules per mole, and that's it.